Okay, students, let's jump into Chapter 3 lecture, okay? Alright, so we're looking at vectors in motion in 2 dimensions. Alright, so what I want to just do is do a quick review over vectors. Now, don't forget that a vector is a quantity that has magnitude and also has direction. Now, as you can see, we can demonstrate an object speed on a flat diagram or on a piece of paper. We can draw it using vectors. That's what makes it very convenient. Why this type of method makes it very convenient in solving problems, because we can physically see it, and two, we can see the not only the magnitude involved of the phenomena, whether it's velocity or acceleration or force or momentum, then we can also see the direction at which the object is moving or the force is applied. Okay, so if, for example, we had an object moving in the northeasterly direction at 5 meters per second, then you may very well draw it and it look like this. Okay, but if we had one that was 10 meters per second, if we had another one over here that was traveling north at 10 meters per second, then it should be twice the length of that vector, okay, because it's twice the magnitude. Okay, so we always represent the magnitude of the vector by the letter without an arrow, okay. So in other words, this is the magnitude of the vector, that value there, and then of course the direction of the vector will be whichever way the arrow is pointing, okay. And so always remember that the magnitude is a scalar quantity, and it can never be negative, okay? Scalar quantities are never negative, okay? It's very important to remember. So we can take 2 different objects, and if they have the same magnitude and the same direction, even though they may be in different places, different starting points, their vectors should be identical. If they have the same magnitude and the same direction, then regardless of where the starting point is, they should have the same. Okay? And of course that makes them equal if they are the same. Now, when we draw vectors and looking at vector addition, of course we have this little algebraic formula here, C is equal to A plus B. Now, how do we draw vectors? How do we know, how to draw them? Again, as I said, previous chapter, it's always tip to tail. Okay, tip to tail. So notice that A touches the tail of B, tip to tail. And so in this case, if you had an object that was 4 miles east of the starting point, and then it went 3 miles north of its the ending point here, okay, then we would need to actually add those vectors to determine the resultant or the actual distance from the starting point. Okay, so how do we do that? Well, we want to find this distance right here. We already know this distance and this distance, but we want to find this distance. All right, well, we do that by vector addition. Now, here again, this is showing you the tip to tail method of drawing vectors. Okay, it's very easy. Okay, so we take E and we move it over here, and you say, can you move a vector? Sure you can. As long as you don't change the magnitude and the direction, you can move it around wherever you want to. Okay, we have a Cartesian coordinate system, and we've got a vector that does like this, then we can move that vector right over here and start at the origin. As long as we don't change the magnitude and the direction, as long as this angle here is the same and the length of it is the same, we can move it around wherever we want to. Okay, all right, and of course it does follow the parallelogram rule like the slide tells you here. And notice that we move the E over here, and it tip to tail. Remember, we're adding vectors, and so the resultant vector then is D plus E. And this is how we draw it. Now, you say, well, what if I left it over here? Well, you could have left it over there. You're still going to get the same result, okay? Because, again, the magnitude and the direction okay, notice there's an angle here, notice that one's at 90 degrees, okay, it's not going to change, all right? Okay, now, so we had these two vectors given P and Q, all right, and let's do the tip to tail method. So here's P, there's P, and then let's take Q and put it over here, and it's going that way. So what would our resultant look like? Well, it should be that right there. So it should be what? It should be A. Okay, and there again, that's adding vectors. Okay, now what about multiplying a vector? Well, it's very simple. All you do is you change the magnitude of it. In other words, if I took A and I made it 2A, then guess what happens to it? It becomes twice the length. Okay, all right. So if I want to take and here they're saying the length of B is stretched by a factor C that it is. B is equal to C times A. So in other words, B is twice A. Okay, so 2A is actually equal to B, or they use the value C, the letter C there, to represent twice as much. Okay, now so we remember when we multiply vectors, we're only changing the magnitude. Okay. We're not changing the direction of it, all right? So that's very important, okay? All right, now, as we said earlier, cannot have a negative magnitude. The only thing we do is when we're subtracting vectors, we change the direction, okay? We're not changing the magnitude, we're just changing the direction, and that's what it tells you here. It's reversing the direction. Which of the vectors is the second in the second row shows A plus B? Okay. Well, all right, if we take A and we do the tip to tail method, okay, A plus B, all right, so A plus B, so which one do you think of A? So we got A, and then we've got what? B, is this correct right here? B, okay, which one's it going to be? Well, of course, it's going to be C, okay, so we got A, and we got B, well, looky there. There's our resultant, okay? So that should be what it looks like. And it's that one right there, okay? All right, now, what about subtracting vectors? Well, basically, the only thing that we do is change the direction of the vector, okay? So to subtract B from A, all right, notice A is in this direction, B is in this direction. Well, what are we going to do? We're going to flip B. So instead of B going this way in a south by southeast direction, we are going to flip it over and make it go a north by northwest direction. Okay, so we're going to flip it 180 degrees. And so your resultant, there it is. That's what it looked like. That would be A minus B. Okay, very simple. Given vectors P and Q, what is P minus Q? Okay, so P is this way, and Q, all right, now notice originally Q is going to the left, but now we are going to flip it and take it to the what? We're going to take it to the right, aren't we? So we're going to go that. Whoops. We're going to go, well, shoot, I didn't mean to do that. There's the answer, of course. It is this one right here. Okay, that's D. Okay, so notice how they flipped it over. So we had P, Q, positive Q is to the left, but negative Q would be to the right. Okay, so here we go. All right. So again, what does that negative mean? That means you just flip the direction. You don't change the magnitude. You just flip the direction, 180 degrees, okay? All right, hope that makes sense. Which of these vectors in the second row shows 2A minus B? Okay, well, 2A, well, that would be twice the length, wouldn't it? Be something like that, wouldn't it? And then minus B. Okay, B originally is this way, but now it's going the opposite way, isn't it? Okay. So would it be this right here? Would it be that right there? Okay, so which one of these is going to match? And of course it's A, isn't it? Yeah. Hopefully you saw that when I drew it. Okay? Yeah. All right. And that's how you do multiplication and subtraction together. Okay? All right. What about using vectors on motion diagrams? All right, well, we use motion vectors for motion diagrams. Again, this goes back to what we've already covered in Chapter 2. The only thing now is we are throwing in the direction, And notice that little arrow over the V, that means it is a vector. Velocity is always a vector component or vector quantity. So is acceleration, so is force, so is momentum, okay? They're all vector quantities. Now, so of course the velocity vector will always point in the direction of the displacement. I mean, I think that's a given. I hope and pray it is. It ought to be. All right, let's say we got a plane moving 100 kilometers due east. All right. A small plane is 100 kilometers due east of Denver after 1 hour flying at a constant speed in the same direction. It is 200 kilometers, all right, due north of Denver. So we started out where we were 100 kilometers east, and then we fly to a point to where we are what? We are 200 kilometers due north of of Denver. So we got 100. We got 200. How are we going to find the plane's velocity? Well, if we drew this, we were 100 kilometers east, and then we wind up what? 200 north, right? And so here's our resultant. Bam, right there. There's where we are. All right, well, that looks kind of like a right triangle, doesn't it? Well, it sure does. It's because it is. Okay? All right, now, so how do we solve it? Well, we use Pythagorean's theorem to find the hypotenuse, and we take the square root of the squares. And we find it to be 224 kilometers. The actual distance from the starting point is 224 kilometers, okay? Now, how would I find the actual angle of that particular going back, how would I find this angle? In other words, how would I find, continue this out, how would I find that angle right there? And remember, you always orient it counterclockwise from the positive x-axis when we are doing direction using vectors. That's just the easiest way to do it. That way you don't mess up on the SIGN, the sign, positive or negative, okay? Well, is it positive? Is it negative? No, just do counterclockwise from positive x-axis to the vector, and then boom. That's all you need to do. Okay, so, well, we just use our arctangent, don't we? We say theta is equal to arctan of y over x. Okay, y was 200, x is 100, and what do we get? We get 63.4 degrees. Well, if we'll go back and look at this slide, that looks like about a 63.4 degree angle to me. Well, actually, excuse me, it's not that angle we measure. I apologize. Boy, I almost goofed, didn't I? Sure did. It's not that angle we're measuring, it's this angle we're measuring, okay? And you say, well, why are you doing that? Well, because, let's see, where am I? Well, shoot, okay? Okay, well, because we were here and we're 100 kilometers in this direction, then in 200 in that direction, okay? So this is the angle we want to know, not this angle over here, okay? All right, very good, okay? All right. Hope that makes sense. Thus, the plane's displacement vector is, and this is how we'd write it, 224 kilometers, 63.4 north of west. Okay, north of west. And you say, how do you know that's north of west? Well, that's how you know. Okay. All right. And actually what we would want to do, since we calculated it that way, we would actually want to go back and say, well, if we come from here over this way, then we would do what? We would actually add it to 90, wouldn't we? Sure would. All right. That'd be what? 153.4? Yeah. Okay. All right. Now, when we're looking at acceleration, acceleration's the same thing, same calculation as it was in Chapter 2, except now we're looking at the as a vector quantity, which it is. I already told you it was. Now, one thing about acceleration, velocity can change in either one of two possible ways. The magnitude can change, indicating a change in speed, or the direction of the motion can change. Okay, so in other words, you can speed up or you can slow down, or you can change direction. Okay, so you can do one of the two. All right. Now, okay, so finding acceleration vector, well, it's much like finding the velocity vector. you take and add your two components, initial and final, and of course, where will the acceleration vector be? Okay. Well, you've got the initial velocity, the final velocity. Well, how do we find the acceleration vector? Okay, well, this would be the average acceleration, okay, because it's the midpoint between initial velocity and the final velocity, okay? So we would call that average acceleration. Now, okay, let's look at vectors in a component system. Now, this is really what I want to start getting into. Remember, I mentioned, I think it was either Chapter 1 or Chapter 2, talking about how we would end up using a Cartesian coordinate system in order to draw our vectors for velocity, acceleration, force, momentum on. Okay, and so we use the coordinate axes, of course, x and y, making it a Cartesian coordinate system. Now, why is this important? Well, because when we start drawing our vectors using this system, it makes the process much easier, because we have the grid system to go by. We can, if we have we have a scale on it, then we know that each particular grid has its particular value, and therefore we can determine our resultant. If we know our x, how far in the x and how far in the y, then we can determine the resultant, okay? Now, we have what are called components, and this seems to always confuse students sometimes, some students anyway. Seems like we have a little bit of a problem understanding what we mean by components. All right, so when we look at this vector, okay, see this vector right here? Every vector has two components. It has an x component and it has a y component. In other words, what do you mean, Mr. Shields? All right, look. If you look at where this vector goes to, right here, that actually is a point in space on a graph paper, isn't it? Right? That's a particular point. Okay, well, what is the x point going to be? Well, that is what we call the component. So it's so many units of x, and it's so many units of y. That particular point has a certain value of x and a certain value of y. Therefore, those are the components of the vector. Now, the component of any vector is simply added, is simply stated as the vector is equal to the a component, the x component plus the y component, okay? So that's simple. Now, it's just some basic rules of remembering when we're doing the component method of vectors. Remember that the absolute value of ax, of the component x, is the magnitude of the component vector ax. I mean, it's just that simple. The sign of ax is positive if it points in the positive x direction, duh, and negative in the negative direction. I mean, come on, y'all. And the y component is determined the same way, okay? If it's in the positive x direction, then it's positive value. Negative x is negative. Same thing, y, positive y is positive, and negative, it's negative, okay? It's really easy to determine, all right? So, let's look at this. The vector is specified, of course, by the magnitude and direction. Here's your magnitude, and there's your direction right there. So, how do we determine then? Well, the component, now look, how do I find the y component of this vector? Well, I use this formula right here. A is equal to, AY is equal to A, which is the magnitude of that vector, the value of it, like 5 or 10 or 2.1 or whatever, okay, times sine theta, okay? And again, we measure our angle. And you say, well, how do I measure the angle? The best way to measure them, that way you don't have to worry about the SIGN, all right? The best way to measure them is to always measure from the positive x-axis counterclockwise, okay? So then I look at my angle, and we should typically, the problem should state it that way, but it won't always state it that way. It may say, well, it's 10 degrees west of north. Well, that is 100 degrees, okay? All right, do you understand what I'm saying? So if you get a problem and it says 10 degrees west of north, then actually the angle is 100 degrees, okay? So please remember that, all right? I did say 10 degrees west of north. Yeah, that'd be 100 degrees. All right, now, okay, so we find our angle. We know the angle. We know the magnitude. That's given. So to find the x component, it's a times cosine of theta. And then to find the y component, it's a sine theta. And it's that simple. Okay? And that gives you the x and the y of the actual vector. It's very, very simple. All right? Now, how do we find the magnitude of the actual vector? Well, if we know x and we know y, then guess what? We can find a using the square root of squares, Pythagorean theorem. And the same way with the angle. How do we find the angle? How do we find this angle? Well, if we know y, if we know x and we know y, well, we just do arctangent of y over x, okay? Okay, that's all we do, all right? And I hope that makes sense. I hope that's you can understand it. All right, so what are the x and y components of this vector? Okay, well, it looks like to me the x is 2 and the y is what, 3? All right, so let's see if we're right. Ta-da! Boy, that was real hard, wasn't it? Okay. Okay. All right, now what about motion on a ramp? When we look at motion on a ramp, anytime you put something and you tilt it, you put it on an incline, then, motion on a flat surface is easy to solve. But motion on an inclined surface, well, guess what? Things change, don't they? The acceleration, the value of the acceleration and the value of the velocity will change. Why? Because of the angle. Okay, because of why? Because of the components of the motion. All right. Why in the world do we use inclined planes? Because it enables us. It does not multiply the work, but it multiplies the force. Okay. In other words, what do you mean? It gives us something called mechanical advantage. The amount of work is the same. It just makes it much easier. Okay. We don't have to use as much force, but we end up having to push it farther. Okay? All right, I hope that makes sense. And we'll get to that when we talk about work. All right, now, okay, so if we want to determine the acceleration of an object on an inclined plane, well, look, how do we do it? Well, we draw our vectors. We say, okay, we got the object is accelerating this way, but it's on an incline. Well, we know what? And I don't really like the way they've drawn this. I'm going to draw it differently. I hope y'all don't mind me doing that, because this way I'm going to draw it. This way I'll draw it with my Cal-based physics. Okay, so we want to know the acceleration in the x direction down this incline. Okay, well, we know that you have what's called a normal force, and we haven't gotten to that yet. And we know that the component of that is in this direction. But now hang on, wait a minute. We know that gravity pulls straight down, doesn't it, towards the center of the earth. And so now we have an angle right here. Well, guess what? This right here, that is the component. This part right here is the same as this right here. Notice the directions are the same. Okay, and the magnitude, I tried to keep them the same. And so you say, well, Mr. Shields, what are you doing here? Well, all right, this is what? This is G, this is G, but this is what? This is G sine theta. This leg over here is, okay? And so I want to find this right here. So how do I find the acceleration? The acceleration is what? It is the opposite over the hypotenuse, okay? Opposite over hypotenuse, and therefore it becomes what? It becomes, let's see, did I do that right? Or did I do it backwards? Yeah, all right. So this becomes what? It becomes G sine theta. So to find this right here, which is this right here, they both match up. Okay, I'm making a mess. All right, so to find it, okay, all right. Okay, we're looking for that part right there and that part right there. This one and this one matches up. Okay, and so this angle is what? Opposite over hypotenuse, right? Because this angle and this angle, geometry tells us they are the same. So I want to find this. So that is opposite, which is sine theta, times the hypotenuse, which is G. Okay, here's G. This is sine theta. G sine theta will give me the acceleration in the x direction. So there's us a nifty little equation for objects on an inclined plane. Okay, and notice they do tell you it's plus or minus. Okay, and since it is going with gravity, it would be positive in this case. If we were pulling the box up the incline, then the acceleration of gravity would be negative. It would be going in the opposite direction. Okay? So instead of gravity helping it to accelerate, it's acting against the acceleration if we're pulling up the incline. I hope that makes sense. And we'll get to this later on, okay? All right. Now, what about relative motion? Relative motion, well, it's what it is. Relative, okay? In other words, just because you're standing still and you're looking at other objects moving, well, based on the position of that object, and based on your position and the position of the other objects that you're watching move, the actual motion relative to you and the earth, or you and that other object, will be different, okay? Will be different. That's why we call it relative. The runner moves at a different velocity relative to each of them, okay? All right, so let's look at a problem. How do we determine this? We use this little simple equation right here. RC being the, I think it tells us here what RC is. Where is it? All right, RA means runner relative to Amy, and then RC would be runner relative to Carlos, and then you have Carlos relative to Amy, okay? So notice how we write our equation. The runner relative to Carlos is equal to the runner relative to Amy plus the velocity of the of Amy to Carlos, okay? So when we add those together, when we go back and whoa, wait a minute, I think they were on there. Yeah, they're on there. So when we look at these values and stick them in, notice what we get. We've got Carlos to Amy is what? 15 meters per second. Runner to Amy is 5 meters per second, right? Okay, so what do we want to find? We know, let's see, we know CA, we know RA, okay? We want to find what? The runner relative to Carlos, okay? Yeah, and so what do? Notice that both of these vectors are moving in the same direction, okay? So what will we do? According to our equation, we are going to add them up, okay? And it would be what? 15 meters, or excuse me, 20 meters per second? Okay. All right, let's move on. Now, what about this situation? What if you have a mouse, and it says a factory conveyor belt rolls at 3 meters per second, so it's going this way. And let's see, a mouse sees a piece of cheese directly across the belt and heads straight for the cheese at 4 meters per second. What is the mouse's speed relative to the factory floor? Okay, this one's really easy because look, the belt's moving this way, the mouse is moving this way. Well, look, y'all, this right here is a what? That right there is a 90-degree angle. Well, we want to know what it is this way. What is the mouse's speed relative to the factory floor? Okay. All right. So what do you mean? Well, if we were on the floor looking at the mouse, how fast would the mouse appear to move? Well, Pythagorean theorem, y'all. We wind up with what? 5 meters per second. Okay? 5 meters per second. It's just simple Pythagorean theorem. All right? Okay, motion in two direction, projectile motion, okay? Projectile motions is probably one of the most realistic forms of motion because motion of an object is typically not always in a straight line. You say even on a flat surface, well, you got to remember something, that flat surfaces on the earth are curved. Now locally, yes, okay? Like in other words, if I'm sitting in my driveway and the driveway's flat, okay, not on a hill, flat driveway, and my car moves 10 feet, okay, relatively speaking, locally speaking, we've got one-dimensional motion there. It's moving in one direction. But if we drive several miles, then the curvature of the earth, even if it was a flat surface, it was out in Kansas somewhere on a road that seemed perfectly flat, well, we know good stinking well it's not perfectly flat. So the car would be moving kind of like a projectile, wouldn't it? Sure would. All right, so when we look at projectile motion, it is an object, of course, that moves in 2 dimensions. And you say, well, can a car be a projectile? Well, on the road, we wouldn't really consider it a projectile. But if we jump a bridge, if we put a ramp up and jump it, then it definitely becomes a projectile, okay? Because projectile motion is under the influence of gravity and nothing else. You mean the velocity of the object coming off the ramp has nothing? Nope, it doesn't affect it. Once you come off that ramp, the velocity in one particular direction is constant. Okay, and if you have constant velocity, it means you have zero acceleration. So, if we neglect air resistance, then projectiles will follow a nice symmetrical path. In other words, if we have a cannon here and we fire this sucker, all right, and we fire a cannonball out, okay, it's going to follow a nice symmetrical path. Okay, it's going to have nice symmetry. All right, notice how this side looks like this side. Well, it's supposed to anyway. All right, so, but we know that's not really the case. In reality, we know there's air resistance, so projectiles will do maybe something like that right there. They'll have a much more, the curve will be much more distorted, okay? It'll come out here and then it may drop off like that, okay? All right, now, okay. All right, so when we look at the components, there's always 2 parts to projectile motion. You have the X component and the Y component. Here's one of those little physics brain teasers. If you take 2 objects and you release them from the same height at the same instant, one is fired out horizontally, the other one is just released and allowed a free fall. Will they hit the floor at different times? Absolutely not. They will hit at the same time, okay? They will hit at the same time, okay? Now, so a couple of things we do need to remember. The horizontal vertical components, I don't want to forget this, are independent of each other. In other words, the X does not affect the Y and the Y does not affect the X. What do you mean? When this object is launched, if you have like a table and you roll a ball off of it, let's say it has a velocity of, I don't know, a velocity of 2 meters per second, okay? When this ball comes off the table, we know it's going to do that right there, correct? Okay. All right, once it comes off this table, we know it's going to start to fall. We've got to remember that the velocity in the X direction, whatever that is, will be the same as its initial velocity in the X direction. The X velocity does not change of a projectile. It remains constant. Therefore, the acceleration in the X direction is going to be equal to 0 meters per second. So then what is affecting the projectile? Okay, well, gravity is. So it is going to be under the influence of G, okay? So that is what affects the projectile, gravity. The velocity in the X direction doesn't matter. Once it becomes airborne, doesn't matter. All right. Okay, again, which one's going to hit first? They both hit at the same instant. All right. Again, don't forget that there are vertical and X components. There are vertical and horizontal components. Just remember that the X component of the velocity is constant. Therefore, there's no acceleration. So you actually only have a Y component. Even when the ball is going up, yes. Remember that the acceleration of an object is always downward when you have a projectile. Always downward, okay? And of course, that's G, negative G. All right, what about circular motion? When we look at circular motion, anytime an object travels in a circular path, we produce something called centripetal acceleration. What do we call that? We call that a center-seeking acceleration. So if we take, say, a merry-go-round, all right, and we look at, let's say, someone sitting on the edge of a merry-go-round, and it's going around and around in a circle like we see here. The acceleration of that person or that object will always be towards the center of the circle, okay? Always, no matter where it is in the path. Now, let's say it has a constant velocity. Let's say velocity of this merry-go-round is constant. Okay. Well, if that's the case, come on now, back up. If that's the case, then what about acceleration? Acceleration should be 0, right? Because, Mr. Shields, you said that anytime we have constant velocity, it means acceleration is 0. Well, not when we have an object moving in a circular path, okay, when it's going in a circle. When we have an object, even though velocity is constant or can be constant, okay, guess what? It still has acceleration. It still has acceleration. And why does it have acceleration? Because, as you notice with these arrows, the direction of the velocity is continuously changing. Okay? Therefore, that causes acceleration. You say, yeah, but the magnitude of the velocity is not changing. You're right. But it still has acceleration because of that fact. Because the direction of the velocity is constantly changing, okay, as it moves through that circular path. Okay, is the car accelerating? Absolutely, it sure is. All right, I don't know why that's there. It's acting really strange. There we go. All right, now how do we calculate motion in 2 dimensions? Okay, how do we calculate velocity? Well, all right, we know that if we look at displacement is what? Well, displacement, d, or x, is equal to the velocity times the change in time, right? All right. Well, all right, so how do we find displacement? Well, if we want to find the actual, all right, what did they do here? It looks like they took d and they substituted the change in velocity over v. Okay, in other words, basically what we're doing here is we are looking at it with respect to velocity. All right, anytime you have velocity over time, and it equals out what? Being velocity squared. Okay. All right, now. All right, and so here's how we get our equation: velocity squared over the radius, which is the actual distance from the center of the circle. Okay. Okay. And they tell you that there. That's called centripetal acceleration. Okay? All right, I hope that helps. All right, and that's the good stopping point right there.